So before we dive full on into the definition of the integral in section 5.2, we want to hit Appendix E and talk about the summation notation or sigma notation. We've used this a couple of times already, but we define the notation I equals m to n of a sub I to be the sum of the sequence terms a sub I starting with m, I equals m, and I ending with I equals n. So this is equal to a sub m plus a sub m plus 1 plus dot 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 a sub n minus 1 plus a sub n. And this is for m less than n. And we've encountered this a couple of times before, but it's really just a convenient way to write out large sums of many different things which all depend or have a pattern between each of the terms. So for example, if I wanted to add up all of the integers from 1 to 100, I could say, oh, let's take 1 plus 2 plus 3 plus 4 plus 5 all the way up until I get to 95 plus 96 plus 97 plus 98 plus 99 plus 100. Or I could just say I equals 1 up to 100 of I. And these represent the same value. And we came across it temporarily, but this is actually equal to 100 times 101 divided by 2, which is equal to 5,050. But what we're going to want to do is kind of manipulate these sums for a bit, because each of these sums, they represent a sum of real numbers, and so all of the classic things which are true about sums are going to be true about these guys as well. But there's a small caveat: the sum has to be finite. Things will work a little bit differently when you have an infinite sum of things, but we don't have to touch that until Calculus 2, the end of Calculus 2. For now, we can just pretend we have a finite sum all the time. Technically, our integrals are going to be infinite sums, but we can turn them into finite sums by throwing a limit out in front. So, for finite sums, the following are true. If c is a constant which does not depend on I, so it could technically even be a variable, but the important thing is that it is constant relative to I, so it does not depend on the value of I. There might be some kind of an outside variable which controls the value of c, but the summation does not change from within. So if I have the sum of a constant multiple of terms, so the c appears on every single term, then I could factor it out, just like I would be able to factor it out on a regular sum. And as a special note, this is also true for infinite sums. If I have the sum of a difference of terms, both of which depend on I, then this is going to be the same thing as the difference of the sums separately. This is something which may not necessarily be true for infinite sums, because in an infinite sum, your sum might be infinite. And so I wouldn't be able to split it up like this, because infinity minus infinity is an indeterminate form. So there's a danger of that. So this is one of the points we have to avoid for infinite sums. However, if I have the sum of a sum of things, this will also always be equal to the sum of the sums of the things. I can split my sums into parts. I equals m up to n of a sub I. Let's add something here. If m is less than p is less than n, then I can split this into the sum from I equals m up to p of a sub I plus the sum I equals m Nope. I equals p plus 1 up to n of a sub I. So this first sum starts from m and it goes all the way up to p, and then the second sum picks up at p plus 1 and then finishes the job up to n. So these are equal. This is sum splitting. And also true for finite sums. See sum splitting. I should have said this is also true for infinite sums. Let's see, if I have a finite sum, then this is equal to sum I equals m to n of a sub sigma of I, where sigma is a permutation function. And what that means is sigma is a function which just scrambles up the order of my index, I. My original sum might look like from I equals 1 to 5 of a sub 5, and this will be equal to, oh, not 5, a sub I. This will be equal to a sub 1 plus a sub 2 plus a sub 3 plus a sub 4 plus a sub 5. But the sum I equals 1 up to 5 of a sub sigma of 5, not 5, of I, is some permutation of the original. So this will be something like a sub 3 plus a sub 2 plus a sub 5, a sub 5 plus a sub 1 plus a sub 4. And I've really just scrambled up the order here, but since addition is commutative, this doesn't change my sum. We might not encounter this, need this property yet, but it is true that if I have a finite sum, I can rearrange my terms in any order I like and add them up that way, which is convenient for simplifying some things, or maybe I need to recombine it with a different sum. This is only true for infinite sums if every term is positive. Because otherwise, since there's an infinity thing here, you can do some really weird stuff and just cheat the outcome of the sum. There's a popular example of a sum which should converge to like natural log of 2 or something, but if you rearrange the terms, you can make the sum equal to whatever you want. So the most important properties we're going to be dealing with are these first three right here. These are our key properties that are going to help us evaluate our definite integrals once we have them defined. So some additional facts. Some of these are much easier to show than others, but the sum of I equals 1 up to n, this is simply equal to, whoops, what are we adding? 1. This is simply equal to n, because I'm going to have an index, I equals 1, I'm going to start at 1, I'm going to end at n, and I'm going to add up 1 for each index. The sum of the integers, I, is equal to n times n plus 1 divided by 2. It's one of the ones we proved on the bonus video. If I have the sum from I equals 1 to n of I squared, this is equal to n times n plus 1 times 2n plus 1, all divided by 6. And if I have the sum I equals 1 up to n of I cubed, this is equal to the square of n times n plus 1 over 2. Basically, it ends up being equal to the square of the sums of the integers, which is a pretty interesting coincidence. Others exist. There is a technique of evaluating the sums of any power of the integers, but typically for our class we're only going to need up to the first 3, because beyond that it gets fairly tedious. Calculus is going to revisit sums in much greater detail. We call them series. An infinite sum is called a series, and we study about how those converge or diverge, and we actually use that to develop special series which are used in the calculation of arbitrary functions. But let's try to use these sum properties on an example we've already encountered. So last time we had f of x equals 4 minus x squared, and we were trying to evaluate the area under the curve. And I had mentioned at the end that if I had taken a limit of my right-handed Riemann sums, I would get something which is equal to the exact area. And I believe, I made a little bit of a boo-boo last time, but I believe we ended with somewhere around the neighborhood of 10.5 as the area under the curve. On the interval from -2 to 2. And I said that the limit as n goes to infinity of r sub n should be the exact area. So let's try to do that. The sum from I equals 1 up to n, I'm just going to use an arbitrary n rectangles, no fixed number. Then I need my Riemann sum formula. So this should look like b minus a over n, let's give this a name, r sub n equals, multiplied by f of a plus I times b minus a over n. So this is equal to sum I equals 1 up to n of 4 over n times f of a is -2 minus 2 plus I times 4 over n. Okay, and since f of x is equal to 4 minus x squared, I'm going to go ahead and plug this into my function. I have 4 over n times what? 4 minus the quantity -2 plus I times 4 over n squared. And I'm going to go ahead and distribute this and multiply it out. I'll have 16 over n minus 4 over n times, let me try to expand this. I'll have 4 minus 8i over n plus 16i squared over n squared. It seems a lot harder when I have n instead of 8, but looks like I have 16 over n minus 16 over n, that's convenient, plus 4 times 8, let's see, 4 is 32i over n squared, okay, minus 64i squared divided by n cubed. That should be multiplied out correctly. But what I'm going to do now is I'm going to try to manipulate what's inside of here with the sum properties in order to try to get one of my basic additional facts that I've listed out above. Because here I see I have an I, and I have things which are not I attached to it, so I could try to pull those off. And here I have an I squared, and I have things which are not I attached to that, so I also want to pull those off. So the first thing I'll do, since I've already multiplied everything out, I'm going to distribute my sum using the second or third sum property, really kind of the same one. So I'll have the sum of 32i over n squared minus the sum I equals 1 up to n of 64I squared over n cubed. Then I can use the first sum property to factor things out of each individual sum. 32 over n squared, sum I equals 1 up to n. Because the 32, that doesn't depend on anything, and the n squared, that does not depend on I. That's decided before we even start doing our sum. So here I just have 32 over n squared times the sum of I, minus, I'll do the same over here, I have 64 over n cubed times the sum from 1 up to n of I squared. Now I have facts for these. These are equal to something. So I have 32 over n squared times, let's see, the sum of I, that's equal to n times n plus 1 all over 2. Then 64 over n cubed. The sum of I squared, that was equal to n times n plus 1 times 2n plus 1 all over 6. I can simplify these a little bit. I can cancel one of these n's with this n, and this 2 with the 32 to get 16. I can cancel a 2 off of the 6, so there's a 3 left over, with the 64 to get 32. And I can cancel one of these n's down here with this n here, giving me 16 times n plus 1 all over n minus 32 n plus 1, 2n plus 1, all over 3n squared. Oops. Squared is what's left over. I could try to collapse this a little bit more, but I'm not feeling up to it quite yet. So this was, if you recall, this is all the way up to the top. This is equal to r sub n. I have a Riemann sum here without any sums. And that's the idea. Because now I can take the limit as n goes to infinity of r sub n, and now it just turns into one of those problems like we had out of section 2.7, or no, it was 2.6. So this is 16 times n plus 1 over n minus 32 plus 1, 2n plus 1, all over 3n squared. Now I can't just plug in infinity because I've got fractions and differences and all kinds of things are going to go wrong. But I can go ahead and try to evaluate this limit. This is now 16n plus 16 all over n, or divided by n, minus, what does 2n plus 1 times n plus 1 look like? I'm going to have a 2n squared plus n plus 2n plus 1. And this is multiplied by 32, so I have 64n squared plus 96n plus 32 all over 3n squared over 3n squared over 3n squared. But look what happens. Those n's cancel, these n squareds cancel, and everything else has at least one n in the denominator. So it looks like I have 16 over n minus 64 thirds plus 96 over 3n plus 32 over 3n squared. And as n goes to infinity, that goes to 0, that goes to 0, that goes to 0. I'm left with 16 minus 64 divided by 3. I'm beginning to get a little concerned because I think this number is not right. So I'll have to go check on it. This is equal to 48 over 3 minus 64 over 3. But that's equal to negative 16 over 3. Which doesn't make sense because this was supposed to be an area. So let's go back and try to find where I made a mistake in this mess. Let's start up here. My function is 4 minus x squared. So I have 4 minus x squared. This is my input. When I square that, negative 2 plus I times 4 over n. I should have 4, minus 8I over n minus 8I over n. There should be 2 of those. Plus 16I squared over n squared. You have to be very careful with these problems because there's plenty of places to make a little numerical mistake. So this, instead of an 8, this should have been a 16. So let me try to follow this as we go through. If that was a 16, that means this 32 should have been a 64. This means this should have been a 64. Leaving that as a 32. Following my mistakes. So let's see what this is supposed to be. I should have gotten 96 over 3 minus 64 over 3, giving me 32 over 3, which is a 10 plus 2/3. Now this fits my other approximations that I got yesterday with my finite sums. So I should expect this value, 10 plus 2/3, to be the exact value of the area under the curve of 4 minus x squared from negative 2 to 2. So next time we'll actually define the integral, and we'll do a couple more of these so that we can get a hang of it.